Hello everyone, and welcome back to another elementary statistics lesson. In this lesson, we're starting a new journey into what is effectively going to be the second part of this course, which is going to be on hypothesis testing. So we're starting chapter 7 here, and essentially what we're working on here is to frame ourselves in our conversation so far is what we learned so far in chapter 6 was we learned how to estimate a population parameter using confidence intervals. So this could have been a population proportion or a population mean, any sort of parameter on the population. And we learned how to estimate that using confidence intervals. In this chapter, we sort of go on the flip side. We say, okay, what if someone comes up to you and gives you a claim, some sort of a statistical claim that they've said about a parameter? How do you accurately check their claim and see if there's any amount of confidence that their claim is true? That's what we're going to be doing. So it's sort of the other side of the coin. This particular lesson is going to be a little bit on the longer side. It's going to be a lot of front-loaded information. So keep that in mind as we go through. There's going to be a lot of discussions and definitions and things of that nature. So to begin with, we're going to note a definition. We're going to note here that, by definition, a hypothesis test is a process that uses sample statistics. So we're going to do something involving small sample sizes in order to test a claim about the value of a population parameter. It may be impossible for you to determine the parameter, some sort of information about a parameter for an entire population. And so just like we did in chapter 6, where we used sample stats in order to gain some insight, we're going to do the same thing here, but in order to check given claims about population parameter. A good guiding example to begin with is the one we have here. So suppose you have some sort of a manufacturer, and it manufactures a new car. And that car, they claim that this car has a mean gas mileage of 50 miles per gallon. You read this and you may or may not question the validity of this claim. So you want to test it. So for example, maybe you have the ability to test, say, 30 of their new cars, and you can obtain a sample mean of, say, 47 miles per gallon. And suppose with your sample, you also determine that the standard deviation of your sample is only 5.5 miles per gallon. The question that you really want to ask is, okay, well, obviously this 47 is different from that 50. However, you only took a sample of 30. So it could be possible that you got maybe a bad sample, or it could be possible that their claim is incorrect. So the question you want to ask is, based on the information you got, does this mean that the manufacturer was wrong in their claim, or does this mean you just got a bad sample? Well, the process for determining whether the manufacturer was right or wrong is kind of counterintuitive. For starters, we make an awkward assumption. In order to determine whether the manufacturer is incorrect, we start by assuming that the manufacturer's statement is correct. If you assume that it's correct, then what you want to do, what we're attempting to do, is we're trying to say, okay, if the manufacturer's statement is correct, does that mean that our sample statistic is unusual or not? If we assume that the manufacturer's statement is correct, and then we can somehow conclude that our sample mean here, that any other sample we take is notably going to be different from the sample that we took, then what that might mean then that our sample is maybe a bad sample. Now, in order to sort of make more mathematical sense about this as we move forward, we need some more definitions. So to begin with, we have here a definition of what's going to be called a statistical hypothesis. This is going to be literally just a super broad definition here. This is just any old statement about a population parameter. the way we're going to move forward is we're going to move forward by every time we encounter some sort of a claim or a situation, we're going to define two particular statistical hypotheses. We're going to characterize any given situation with a pair of statements that describe the situation in complementary ways. What that means is that one of them have to be true. And if that doesn't happen, basically what we're saying is that we're going to set up two statements such that if one doesn't occur, the other one has to occur. So that means that it's sort of binary. There's only two options. The way we're going to set that up is we're going to, every time we encounter a given situation and we build out these two claims, we're going to give those claims names. We're going to call one the null hypothesis, and we're going to call the other one the alternative hypothesis. Broadly speaking, the reason the null hypothesis is called what it is because essentially this is used in statistical inferencing where you have some sort of a situation and then some sort of a change has occurred, and what you're attempting to do is you're attempting to deduce whether under a certain change a desired outcome has occurred. And so the null hypothesis, the word null, generally gets reserved for the statistical statement that says that nothing interesting happened after you changed it. That is null. Nothing interesting happened. Whereas the alternative hypothesis says, okay, well, what's the other option of nothing interesting happens? The alternative is something happens. So that's the reason these names are used. But for our purposes, you don't have to worry too much about where the names come from. We're just going to accept that the null hypothesis we're going to call H naught or H sub 0. This is going to be any statistical hypothesis that contains a statement of equality. What that means is candidates for this are going to be less than or equal to, or greater than or equal to. The alternative hypothesis is what we're going to call H sub A. This is literally going to be the opposite. So if H sub 0 is, say, less than or equal to, the complete opposite to being less than or equal to is, of course, being strictly greater than. If H naught is equal, then HA will be not equal. And if H naught is greater than or equal to, then the opposite of that is strictly less than. So together, H naught and HA handle any possible conclusion given us any situation. Either HA needs to occur, or either H0 needs to occur, or HA needs to occur. Because at the very least, any given number is either going to be less than or equal to, or strictly greater than type thing. Now, there's a lot of different combinations for how these two statements can go together. This is a table that can help sort of organize your thoughts. So remember that our definition is that H naught will contain statements of equality. Okay? So the sort of options we have at our disposal is H naught might contain something like mu is greater than or equal to k. And there's a couple ways that you can, in English, refer to this sort of mathematical representation. You could talk about H naught being greater than or equal to k, at least k, not less than k. And then the complementary statement to being greater than or equal to k is, of course, mu is less than k. Not just less than, but strictly less than. And those are the statements we have over here. Less than k, below k, fewer than k. Similarly, if we flip all of these inequalities, it sort of trades out the math statements, and it trades out the English as well. Here, H naught mu is the null hypothesis here is mu being less than or equal to k, so there's less than or equal to k, at most k, not more than k. Where the complement is strict inequality, and here the alternate hypothesis is that our mu is greater than k, above k, or more than k. Equality, at the bottom here, we have the null hypothesis is mu equals k. Of course, there's a couple ways to write that. And then the alternate hypothesis, the opposite of being equal to k, of course, is not being equal to k. or different from K, or not K. So again, to frame ourselves in what we're attempting to do here, we're going to start with a given claim that some sort of a company has put forth, and then we're going to interpret that claim in a sort of binary sense. We're going to declare a null hypothesis and an alternate hypothesis so that one or the other has to be true. And then we're going to figure out how to mathematically apply a number to a probability that one might be true. But to begin with, let's get some experience converting English words into math statements. So here we have the beginning of an example that's going to run through this entire lecture. We have here that for number 1 here, a school publicizes that, and here I'm going to underline this, the proportion of its students who are involved in at least one extracurricular activity is 61%. You should interpret this. You see the word is, so that means there's some sort of an equality running around. You see the word proportion, so that means a p-value is going to be, I shouldn't use the word p-value, but the letter p is going to be there in terms of population proportions. And what this underlined statement is telling us is that p is equal to 61%, otherwise known as 0.61. The complementary, or the opposite statement, is of course p is not equal to 0.61. So now we need to take a look at these two claims and label one the null hypothesis and label one the alternate hypothesis. But remember that the null hypothesis, by our definition, if we come back up here to the definition, the null hypothesis, H0, always contains equality. So the minute you write out what the math version of this English statement is, we know that H naught, the null hypothesis, is always going to be the one that contains equality, and then the one that doesn't contain equality is going to be the alternate hypothesis. Once you write out the null hypothesis and the alternate hypothesis, we then need to choose one of these two options to be the claim that's being put forth. The school is making some sort of a claim, and their claim seems to be the equal statement. So, importantly, this is the claim. This is going to be important to determine which one's the claim, because which one's the claim is going to depend on, or rather, which one's the claim is going to characterize how we try to mathematize our conclusions as we try to either accept the claim or reject the claim. The next example has us looking at a car dealership that announces that the mean time for an oil change is less than 15 minutes. The word mean tells me that there's going to be a mu, and an oil change is, we read the word less than, that implies that it's going to be strictly less than 15 minutes. Remember that the less than symbol goes with the non-equal hypothesis, which is the alternate hypothesis. So what that means here is that as we translate this statement into either the null hypothesis or the complementary, we're going to end up with HA, the alternate hypothesis, being mu is less than 15, and then the complement of that is the null hypothesis, mu being greater than or equal to 15. Where here, the car dealership's claim seems to be representing the alternate hypothesis. It's important to realize that whether the claim, or rather I should say, it's important to realize that whether something is going to be the alternate hypothesis or the null hypothesis is dependent on whether it contains an equal sign or not. This does not contain an equal sign, so it's the alternate. This does contain an equal sign, so it's the claim. So it's the null hypothesis. And then the claim gets attributed based on how who's making the statement, and rather what statement they're making. Number 3 here Makes it claims that a company advertises that the mean life of its furnaces is more than 18 years. Mean, again, means mu, and more than 18 is greater than 18. I do not see in greater than or equal to. What that means is that the claim here is actually the alternate hypothesis, and the opposite is the null hypothesis, which in this case is mu is less than or equal to 18. Or again, the claim made by the company in this case is the alternate hypothesis. So what we're learning right now is we're learning how to take claims made by individuals or companies, some sort of a statistics claim right here. Each of these represent a claim that has been made about a population parameter. And what we're doing is we're trying to characterize the mathematical statement that they're making. And then from there, we're trying to then label their claim as either the null or the alternate hypothesis, which now we're going to move toward trying to find with some amount of probability whether one is true or not. To do that, we need to talk about types of errors and levels of significance. Now, I mentioned this before, but no matter which hypothesis is representing the claim, and this is really important but admittedly a little difficult to wrap your head around first, you always have to start by assuming that the equality condition in the null hypothesis is true. We mentioned this before, but in order to turn around and try to either support or reject a given claim, we assume that the claim is true, and then we're going to run some sample statistics on basically saying, if the statement is true, do things break? If the answer is yes, then the statement couldn't have been true. If the answer is no, then you say, okay, well, then the statement might be true. So we're going to start with assuming that the equality condition in the null hypothesis is true. And then once we run through our mathematical statistics, we get to do one of two things. Either we get to reject the null hypothesis, or we fail to reject the null hypothesis. Note that there's a lot of subtleties going on here. Because our decision, whether we reject or fail to reject the null hypothesis, is based on a sample and not the entire population, as we mentioned in the very first example in this conversation, there's always the possibility, I should underline this, there's always the possibility that you make the wrong choice. For example, you may reject a null hypothesis. You may turn around and say, the null hypothesis is this claim up here that, that the mean life of a company's furnaces is less than or equal to 18 years. You might turn around and reject that and say, no, that's not true. When in fact, the actual population data is that it is true. You just got a bad sample. Or, conversely, you might encounter a different situation. You might end up failing to reject a null hypothesis when that null hypothesis was actually false. That is, you accepted a claim when it wasn't actually true. Both of these can occur because you have bad samples. However, the real-life consequences of these are usually pretty substantial. So we give these names. We're going to declare a type 1 error to occur if the null hypothesis is rejected when in fact it was true. And we're going to call a type 2 error to be the type of error committed when the null hypothesis is not rejected when it in fact was false. To help organize sort of what type of conclusions are occurring in your brain, we have a table here. Focusing on the null hypothesis can either be true or false. And we're talking population-wise. If you zoom out and take in all the data, either the null hypothesis is true or false. Based on a sample that you take, we will figure out how to mathematically determine whether we should reject H0 the null hypothesis or not reject it. If, for example, for the population, the null hypothesis is true, and we chose to accept it, we chose not to reject it, then we've made the right choice. That's a good thing. Check mark. Similarly, if the null hypothesis is actually not true for the population, and then according to our math on the sample, we determine that, oh, look, we're actually going to reject it because we don't think it's true, then again, we made the right decision. However, if the null hypothesis for the population is not true, but you accept it, that will incur a type 2 error. And if the null hypothesis was true, but you actually ended up throwing it out, then that incurs a type 1 error. Now, how we determine whether we should or should not reject the null hypothesis, this is something we're going to learn as we move forward. Oftentimes, by the way, if this is confusing at all, there's a strong analog between the content up here and the United States judicial system. So in the United States legal system, right, an accusation is levied against a given party. We assume that the defendant is innocent until proven guilty. So we're going to call the null hypothesis H0. We're going to call this assumed innocence. Then the burden of proof lies on the prosecution. And then we say that if there is not enough evidence, then we declare the defendant not guilty. But you should note here that declaring a defendant not guilty does not in any way imply that the defendant didn't commit the crime. It only implies that there was insufficient evidence. So the conclusions we can draw are the following. Truth about the defendant, which this of course is that null hypothesis. If the defendant was innocent and we rendered them not guilty, then justice has been served. If the defendant was guilty and we declared them guilty, then again justice is achieved. If the defendant was guilty and the verdict was not guilty, then we commit what we're calling a type 2 error. Whereas if a defendant was innocent but we declared them guilty, this is a type 1 error. Where we might note that type 1 and type 2 errors, some are better or worse than others. In this case, of course, a type 1 error means that we convicted an innocent person. This is really bad. A type 2 error means we did not convict a guilty person. For the purposes of our judicial system, a type 1 error is regarded as worse than a type 2 error. But if this sort of characterization of type 1 and type 2 errors and null hypothesis and whatnot helps you understand the situation, this is a good analog to build. So here's another example. It's not necessarily the legal system. This has to do with USDA limits for bacterial infections. So here what we're saying is that the USDA limit for salmonella contamination for chicken is apparently 20%. The minute I read this, by the way, moving forward, the minute I read this, I want to start mathematizing it. So what we're going to do is we're going to let P represent the proportion of chicken that is contaminated. And the minute that very first line, well, let's continue reading, says that a meat inspector reports that the chicken produced by a given company exceeds the USDA limit. So the claim is that P, the proportion of chicken that is contaminated made by this company, the claim is that more than 20% is contaminated. What we'd like to do is perform a hypothesis test to determine whether the meat inspector's claim is true. The minute I read this English sort of paragraph and I'm start mathematizing it, I've come up with the appropriate letter, P, of course, because I read the word proportion. The claim is that more than 20% is contaminated. So if I want to then turn around and develop a null hypothesis or an alternate hypothesis, I have two things I need to build. H0, which is saying something about P, and HA, which is saying something about P. As soon as I read, however, more than 20%, what that means is that this is a greater than inequality. So that'll have to become the alternate hypothesis. So this is going to say P is greater than 20%, otherwise known as 0.2. So maybe we'll erase that real quick. And the complete opposite of being strictly greater than 0.2 is being less than or equal to 0.2, where here we'll note that the claim made by the health inspector is going to be attributed to the alternate hypothesis. So now what we're going to do is we're going to do some amount of mathematics in order to convince ourselves that we should or should not reject H naught. Those are the only two options we get in this entire process of hypothesis testing. Either we accept H naught or we reject H naught. The result of one of those conclusions will then inform us about what happens to the claim, which in this case is the alternate hypothesis. So what we want to do here is we just want to ask ourselves what type 1 and type 2 errors look like here. So in this case, what we're going to note here is that a type 1 error occurs when, if you reference the definition, when the actual, as in instead of looking at a sample, you were to zoom out and look at all of the chicken being made, when the actual proportion P is less than or equal to 0.2, but unfortunately you chose to reject the null hypothesis. So H naught right here is P is less than or equal to 0.2. If you, through the math that we're going to learn next section, if you choose to reject H naught and claim to the public that, no, this can't be the case, but in all actuality, it really is the case, this is a type 1 error. And what's more is that the real-life ramifications of this might be what? Here, you might cause some sort of a health scare. Because the P, proportion of contaminated chicken, is actually pretty low, but by rejecting that statement, you're declaring to the general public, oh no, it's actually pretty big. And this might be concerning to them, so there might be a health scare. Moreover, economically, it might hurt chicken sales. So this sounds like a pretty bad error to commit, as far as we can tell. What is the other type of error, though? Let's see. A type 2 error occurs when actually the proportion of contaminated chicken is larger than 0.2. However, you chose not to reject the hypothesis, the null hypothesis. So here, this will occurs when actually P is greater than or equal to 0.2, but you do not reject H naught. Now remember, not rejecting H naught doesn't necessarily mean you accept H naught, but to the general public, they'll sort of view it that way. So the way that this will work is apparently the contaminated chicken is actually fairly high, but by not rejecting H0, by not rejecting that it's this low, you're effectively telling the community that it's probably pretty low, even though it's pretty high. This is a concerning error to run into, because here you are allowing contaminated chicken to be sold. And you essentially told people not to worry. That's concerning because this could actually lead to the death of people. If they don't think something's wrong, but in all actuality something is, they could be going out purchasing some contaminated chicken and then dying. So in this example that we've built here, a type 2 error, the death of people, is somehow more serious than hurting some chicken sales. As a company, you have to be a little concerned about type 1 or type 2 errors. So when this reporter, this health inspector, makes this bold claim, and then the company wants to turn around and refute this claim, what they're going to do is they're going to go to their statistician, and they're going to say, look, can you run some sort of a statistical analysis to determine the validity of this inspector's claim? And it's important that the statistician, as they go through their hypothesis testing to see if this claim is true or not, it's important for the statistician to know and be wary of type 1 and type 2 errors, not only what they mean and how they occur, but what the literal real-world ramifications are for them, because this will inform the decision that the statistician returns back to the company. Now, what we need to do is we need to move forward in this conversation and really start taking a crack at understanding how to mathematically determine whether we reject the null hypothesis or not. That's what we need to be able to determine. Rejecting the null hypothesis is going to be dependent on some sort of a probability that we're going to assign, and it's going to essentially be related to the probability that if this was true, how likely it would be that other samples would match the claim. If that probability is low, then probably this claim wasn't true in the first place, and so we can reject it. If, however, the probability is pretty high, then we have insufficient evidence to reject the null hypothesis, and therefore we might have to accept it. The rest of today's lecture is going to introduce that notion, but we're going to pause here for this video, and we're going to resume next video trying to answer this exact question.